which is because it is a tree. If I allow myself to share subtrees, then, of course, I don't have a tree anymore, but it's a perfectly valid graph, directed acyclic graph, and it has the same information as far as I'm concerned. In particular, all those T's over here, why do I have to have 5 T's and 3 F's? They all represent the same information, so I can just contract all the T's to a single node, still have all the edges go to that single node, so just merging all the T's. But I can go on. I can go do better than that. Right? Because these R's over here don't do anything. Whether they are true or false, it doesn't matter. I always get to true anyway. So I might as well omit them from the tree altogether. Doesn't change what the tree expresses. Same for the Q over here. Yeah, also doesn't matter whether it's true or false. And the R over here also doesn't matter if it's true or false. In other words, there's another tree. Actually, it's not a tree anymore, but we're still calling these things trees, which is maybe a bit confusing. But there's another tree, I will call it tree, which represents the same information. Where are my pens? Maybe this black is better. We still start with the P, and to say if the P is true, I can go down to true straight away because I know I'm done. If P is false, then I have to evaluate Q. If Q is false, then I know I can never be true anymore, so I can go to false without evaluating R. If Q is true, I still have to evaluate R, and then, depending on whether that is true or not, I get to true. This graph, which is not a tree, it's a directed acyclic graph, represents the same information as far as I'm concerned right now as the one I started with. I think you agree this is more compact. It's nicer. Okay, that is the core realization behind binary decision diagrams. Okay, systematically done. First merge the leaves, which gives you this tree over here. Then merge those nodes that have exactly the same children for their true and false branches. Which are those in this tree?
The left R.
Yeah, the 2 R's over here. They have the same branches.
Right.
Sorry?
Also the left one. Left
No, okay, yeah. So actually, there are two rules, and maybe you can apply them both here. So that's a bit confusing. These 2 R's, if you compare them to one another, and you look where the true branches go, you see the true branch of these 2 R's go to the same place. The false branch of these 2 R's also go to the same place. Therefore, I may merge them. Yeah. There's another observation that says, yeah, but the true and false branch actually go to the same place anyway, so I can't just merge them, I can omit them altogether. That's a different rule, and both of them apply here. So in that sense, it's not such a good example. If you omit the spurious R's, then only one of the R's is left, and now you see that there's a spurious Q and Q as well. So we get to the thing that was already on the whiteboard. Definition. A binary decision diagram is a root directly acyclic graph. Lots of words, but it's just the thing that I showed on the board. Every leaf node is labeled either true or false. Every non-leaf node is labeled with a proposition. Every non-leaf node has 2 outgoing edges, one for true, one for false. And every path from a root to a leaf has only distinct propositions. You never meet the same proposition twice, that wouldn't make sense. That's a binary decision diagram. An ordered binary decision diagram is one in which the proposition will always occur in the same order. We're only going to talk about ordered binary decision diagrams. A reduced ordered binary decision diagram is an ordered binary decision diagram that is reduced. Wow. What does it mean to be reduced? Well, actually, all the redundancies that I discussed are no longer there. We just got rid of all of them. So all leaf nodes are distinctly labeled. That means there are only 2 leaves because they're labeled true or false. The outgoing edges of all non-leaf nodes go to distinct nodes. So I can't have two non-leaf nodes that have the same false child and the same true child. Then I need to merge them. Finally, all distinct non-leaf nodes, I switch those two around. The outgoing leaf edges of all leaf nodes go to distinct nodes. So if I node and my true and false branch don't go to the same node, otherwise they're not reduced. Yeah? And the last one is the one I said before. If there are two non-leaf nodes, then either their true branches go different places or their false branches go different places. If neither is the case, then I should merge them. Right, so
what
yes.
does compatibly ordered mean?
It means that, look, if I take this branch, then I only ever meet P. If I take this branch, then I meet P, then Q. If I meet this branch, then I meet P, Q, R. Compatibly ordered means I can never, along one path, meet two propositions in one order and along another path in the other order. I could also say you always meet all propositions in the same order, but you don't always meet all propositions, so that would be slightly wrong. But that's certainly
if
the
you
intuition.
meet once, you meet first P and then Q, then you
Yes.
always have to meet them.
Yes, then you will never first meet Q and then P. What you can also think of is just the whole thing is layered. The way I draw it is actually layered. This is the layer of P, this is the layer of Q, this is the layer of R. Edges always go down. So that's another way to guarantee that. Okay, good question. So I will omit the word ordered from now on because everything will be ordered in that sense, but not everything will be reduced all the time. But I do want to work with reduced binary decision diagrams because they're nice and small. At least sometimes they're nice and small. Here is an interesting observation. If I have a formula, and if I choose an ordering of my proposition, then there is only exactly one ordered reduced BDD encoding the formula. Is that, can you see why that is? I think you can see why that is. You pretty much mechanically build the thing, right? You can even do it by first building the whole binary tree and then reducing it. There's only one way to do that. So, what does that mean? If I want now if I have two formulas, suppose I want to establish whether two formulas are logically equivalent. I claim I can use binary decision diagrams to show that. Yeah? Do you see that? Lars, do you see that? Because of this property.
Not
No?
really, no.
Mark?
Yes.
Yes, how do you use
They
this?
must have the same ordered.
Yeah, same BDD, same reduced BDD. Yes, exactly. If I have two formulas that are logically equivalent, and I built their reduced BDDs, then they must be isomorphic. If they're not isomorphic, then the two things weren't logically equivalent. If I want to establish that a formula, whether or not the formula is valid, how can I do that using the BDD?
There should be no possible outcomes of resolving false.
Yes, so, and if it is a reduced BDD, what does that mean?
There's no false also.
There's no false, but it means even more.
The root is true. It's just
Yes.
true.
Yeah, there are actually only one node, which is the root and the leaf, and it is labeled true. Is it also what you were going to say? Yes. So the BDD of a valid formula is the simplest BDD you can think of. It has one node and it is labeled true. What about satisfiable formulas? How can you see from the BDD that the formula is satisfiable?
True is reachable.
True, it occurs in the tree. Yeah, it's reachable. Exactly. So this BDD representation, you can meet the same terms and concepts that we met before, but now in terms of the BDD. Yeah, so that's actually what's on the slide as well. Equivalence of two formulas means that their BDDs coincide, their reduced BDDs coincide. Validity means that the BDD equals that of true. In other words, consists of only one node and that is labeled true. Satisfiability means it has a T node. Now, the interesting thing about BDDs is that they can be very, very small with respect, if you compare it to the truth table. It can really be quite small. But interestingly also, it actually depends quite a bit